So my name is Alexandre Rodrigues. I am pursuing a PhD in the doctoral program of electrical and computer engineering at IST. It's part of the Universidade de Lisboa, or University of Lisbon, and I'm affiliated with RISC-V. And so I'm going to be presenting our work that we published in CHESS, which is accelerating NTT with the RISC-V Vector extension for fully homomorphic encryption. So this first part, I'm mostly going to gloss over, since I assume most people are already very familiar with FHE, but it has important use cases in terms of privacy. So you can do computation on things like medical records, which are subject to regulations. And so you must either trust the server that you're doing the computation on, or you can take matters into your own hands and perform fully homomorphic encryption, which enables your computing to be truly private, since all of the operations are going to be performed on encrypted data. You might also know that this has a very high computational cost. It's typically over 4 orders of magnitudes than if you were to do the computations on unencrypted data. And so it's very valuable for you to accelerate this process. Now, at the core of FHE is the number theoretic transform. Since FHE relies on the ring learning with errors problem, which needs polynomial multiplication, and this polynomial multiplication has an order of p squared, where p is the order of the polynomial you're working with, and the order of the polynomial is typically quite large. With NTT, however, you can reduce the complexity of the whole problem to p log p, which is much better, and the multiplication itself is reduced to linear time, so it just becomes OP. Now, the memory accesses for most NTT algorithms are quite complex. Here to the right, you see the memory accesses for Cooley-Tukey with a small p as an example of 8. And so these algorithms are typically quite challenging to vectorize, and they require scatter-gather memory accesses, which are typically not super good for performance. And their complexity typically means the compiler can't really reason about them, and so it can't really auto-vectorize your code effectively. RISC-V is a free and open source instruction set architecture standard. The specification is fully open source, and so you can implement a RISC-V processor at no licensing cost to you. So its main advantage is the fact that the design is modular, and so this makes it quite flexible. You can pick from a variety of base sets, ranging from the embedded with only 16 registers to 32, 64-bit, and you can put as many extensions as you want on top of that, from floating points to vector extension, and you can even add your own custom extensions. RISC-V right now is experiencing rapid adoption, and so it's a great opportunity here. So there's a lot of funding initiatives from governments, such as the EPI and DARE projects. There's also investments from big names in the industry, and it has use cases ranging from supercomputing to embedded and passing through automotive and so on. So it's booming right now. Now, important to this work and to RISC-V is the RISC-V vector extension. So this extension allows you to do SIMD computation. You have access to 32 vector registers, and the vector length that your architecture has is you can choose from a range of vector lengths. So it's microarchitectural. It's specific to your processor. You can get very large, up to 64K bits. But it's not necessarily tied to the processing width. So you can, for example, have a very big vector register with a very big vector length, but you don't need to process everything in one cycle, right? So you can split it up and process it in chunks, basically. You can configure the element size and the element type at runtime. This allows you to have architectures such as the two you see on the right. So the top one is a 256-bit vector length, and here we've configured it with 64-bit elements. And this one processes every element in a single cycle. Meanwhile, the architecture below is 16 kilobits, but it only has 8 vector lanes. So if you configure it with 32 bits, that's 512 elements, but you only process 8 elements at a time. You can write vector length agnostic code with RVV, meaning you can take the same code and run it efficiently on the top architecture or the bottom architecture or any hardware with any VL, any vector length. And it does have support for masked operations and for scatter-gather memory access, which is important for algorithms as complex as the NTT and INTT. Currently, there's two major versions in circulation. There's the previous sort of trial version, so to speak, which is RVV 0.7.1. So that was not a final version, but some hardware ended up coming out that implemented it, and it's still in active circulation. And there's, of course, the solidified standard, which is RVV 1.0. Now going back to FHE and NTT and INTT algorithms. So first, taking a look at Cooley-Tukey NTT and Gentelman-Sande NTT, which are quite similar to each other. So these algorithms are fairly simple, they're reasonably fast, and for those reasons, they're in use in libraries such as OpenFHE. To the right, you see the memory access pattern again for Cooley-Tukey, and the access pattern for Gentelman-Sande is basically the same, it's just inverted, it's just the other way around. So these variable access patterns make it quite challenging to vectorize, and they do require some masking of some vector lanes, which is not great for performance. You lose some vector utilization as a result. Now, Korn-Lambiotte and Pease, NTT and INTT, respectively. As you see on the right, they have the constant memory accesses. So each stage has the same elements being accessed in the same pattern, and this is quite SIMD friendly. So it's a bit easier to write SIMD algorithms for it. But we also see that the input and output indices differ, which is different from Cooley-Tukey and Gentelman-Sande, meaning you can't program it in place. You need a little auxiliary vector, which is a small disadvantage, everything else considered. So we vectorized Cooley-Tukey and Gentelman-Sande, the first two algorithms I mentioned, creating three-stage algorithms for both of them. So these use the masking feature of RISC-V, and they're programmed in place, meaning we don't need an auxiliary vector here. Now the memory access pattern varies with t, depending on the stage. And so t starts at a value of p over 2. So here, given we have a p of 8, t starts at 4, and then you divide it by 2 in every iteration. And so this value of t dictates which stage you're in. And stage A, which is the first one that we have depicted here, is when t is greater than half of the vector length, which is the case. Half of the vector length is 4 here. And so what happens here is you have regular loads and stores, and you have full vector utilization. So if you think of the callers as different vector registers, you see that you can take, imagine you have a vector length of 4 in this example. You can see that you can load the blue into a single register, you can load the green in another register, you perform the butterfly, and then you do stores in the reds and the yellow section. And so very simple vector codes, you just do regular loads, a regular store. As t decreases, and so when it's between 1 and half of the vector length, we see that there is now some overlap between the registers. So you can still do regular loads. You load the first 4 elements, and then these other 4 elements, which starts halfway into the previous one. You can still do regular loads, but then we do masked stores in order, of course, not to overwrite the correct values. So if you look at the arrows here, we see that we can only write these first 2 and then these second 2 for the 2 halves of the butterfly. And so what happens is we get partial vector utilization. Since we're masking half of the vector units, we don't get as great of a performance. Now for stage C, which is only on the very last stage of the algorithm, this happens when t equals 1. We can do strided loads and strided stores. So as you see, we have a stride of 2. So one of the registers is every 2 elements, and the other is every 2 elements shifted down by 1, essentially. And we can achieve full vector utilization. Strided loads and stores are not as efficient as regular loads and stores, but the performance is still better than masking half of your vector lanes. Now, we also have vectorized implementations for Korn-Lambiotte and for Pease, which you see above and below. We also developed three-stage algorithms, but here the stages are not to do with the memory access patterns on the polynomials, but on the roots of unity. So we do require an auxiliary array since we can't program this in place, but we don't need masking, so we achieve full vector utilization in every stage. The roots of unity access vary with M, and M, depending on the algorithm, is initialized and changes differently. So for Korn-Lambiotte, as you see above, we can do regular loads, but then we do strided stores on every stage. M starts with a value of 1, and it doubles every stage. Pease is the exact opposite. So we do strided loads and regular stores. M starts at P over 2, and you divide it by 2 on every stage. So now we can see how we do our roots of unity access. So when M equals 1, which is the start of one algorithm and the end of the other, only one of the roots of unity is used. And so we can do what's called a vector broadcast, which is very efficient. You just load one element, you split it across the vector, and then you can use the vector just fine. When M grows past 1 but is under the vector length, then you have to gather some of the elements of the roots of unity into the elements of the vector with a certain pattern, and you can pre-compute this pattern before the algorithm. So it's very efficient. You just load this pattern and you use the vector gather in order to pick and choose which values you want, essentially. Now, when M grows further past or equaling the vector length, we see that the roots of unity are now too large to fit in a single vector register. Here, the vector length is 4, as you can see. But you have the benefits of that you can do a vector load. So now the loads are contiguous. You just take these values, you do a normal load to each of the vector registers. One thing we do to increase efficiency is reuse the roots of unity. So we only load them once, and then we use them for a number of iterations. And so essentially what we do is, instead of going to the inputs and figuring out what roots of unity we need, we load the roots of unity and we figure out which of the inputs are going to need these roots of unity. This requires a bit more complex indexing into the input and output, but the performance is still great. And because the regular or strided accesses to the polynomial still remain. You might have noticed that in this case in particular, it doesn't make much sense to load it in 2 vector registers. As you can see, they're going to have the exact same contents, right? So between 4 and 7, they're going to be in the 2 registers are going to have the exact same content. And so this is a special case when M equals the vector length. And we do handle this special case. So we only perform a single load. We only use a single register. But of course, we can't keep doing this, right? As M grows further, they're no longer going to have the same values. So this is just a single special stage that we do handle. Regarding the modular reduction. So as you know, the polynomial coefficients are between 0 and your modulus, which is Q, and you need to maintain it below that modulus. But of course, you don't want to use the modulo operator because it's very, very slow. And so you can use a few tricks. So for multiplication, you know that if you multiply two elements of the polynomial, you know that the result is going to be below q squared. So you can use something called the Shoup reduction, which effectively does modular reduction on values within this range. As for addition, you know that the result is going to be below 2q, and so you can just use a very simple modular reduction, which is essentially a subtraction. And here we can use the masked feature of RISC-V to great effect. So here at the top, you can see, for example, imagine you perform an addition, and some of the elements are going to be below your modulus, which are fine, and some are going to be above, which we need to reduce. And so we generate a mask by comparing with the value of q, which is going to enable the lanes in which the value exceeds our modulus. And so later we can splat the modulus into another vector. We can use this masked in order to do a masked subtraction. And essentially, you only do the subtraction on the elements which you want to reduce. We integrate our implementations in OpenFHE, which is an open source FHE library, which is in active development. It supports a variety of FHE schemes, and this allows us to evaluate our implementations in a full FHE context. And allows us to validate our results and to evaluate the speedups of whole applications, not just the NTT and INTT. So we compile OpenFHE for RISC-V, and we replace the NTT and INTT calls with our implementations. We link everything together, and that allows us to test them out in this whole context. We test two experimental platforms. So we have a vector processing unit, or a VPU, which is the Vitruvius Plus design. It's the architecture you see at the top here. So it runs the older 0.7.1 standards. It has a large vector length of 16 kilobits, which with a 64-bit configuration is 256 vector elements. It has 8 vector lanes, so it's similar to that architecture I described previously, in which you have a long vector, but you have a smaller width of processing. So each of the vector lanes can do one double precision operation per cycle. It is prototyped on an FPGA, but this same design has previously been taped out on a physical 22 nanometer process. The other architecture we test is an out-of-order processor. So this is tightly coupled with the core. It works more like AVX or SSE. If you're familiar with x86 vector instructions, it works basically like that. It runs RVV 1.0, and we configure it with a variety of vector lengths ranging from 512 to 2 kilobits. And we also try between 1 and 2 vector units. And each vector unit can operate on the whole vector in every cycle, as you see here in this example. It is simulated in GEM5, the out-of-order processor model, which is a cycle-accurate architecture simulator. And we try to configure the microarchitecture to match as closely as possible a Xeon Gold 63312U, which you're going to see is going to be a relevant architecture as we do compare the performance to it. So this first comparison is for the speed up of the vector implementations versus the scalar implementation. This is running on the VPU, which is implemented on the FPGA. And here we have depicted the NTT speedups, but the results are very similar for the INTT speedups for the respective algorithms. So Cooley-Tukey is very similar to Gentelman-Sande, and Korn-Lambiotte is very similar to Pease. We see that Korn-Lambiotte, it's a bit more complex, and so it is not as efficient on the first stages. But we see that, if you recall, Cooley-Tukey has a stage where it has approximately half the vector utilization, and so we see that its speedup drops quite significantly in certain stages. And so Korn-Lambiotte, if we look at the overall speedup, despite the fact it has a little deficit at the start, the overall speedup is much greater than Cooley-Tukey and Gentelman-Sande. Here we compare the speedup versus the state-of-the-art library on the Xeon processor. So here we're comparing the VPU, the performance on the VPU. The state-of-the-art library is Intel Hexel, which is state-of-the-art on x86-64, but it does require the AVX512 IFMA instruction set extension to get maximum performance. And this extension is not super common. There's not many processors which implement it. So here at the right first, we have the peak performances of the two architectures shown. So the peak performance of the VPU remember, we have 8 units. Each unit, if you consider a multiply add, that's 2 operations. And so you can get 16 operations per cycle. And we do the exact same analysis for the Xeon Gold processor, and we see that it has exactly triple the peak performance. And despite the fact it has a lot higher of a performance, we see that our implementation outperforms it in terms of speed up for values, polynomial sizes exceeding 16K. So we see that we have better performance for 16 and 64K. And we also seem to see a trend here that as the polynomial size increases, the performance of our implementation on the long vector VPU increases, while the performance on Hexel on tends to decrease. We also compared the NTT and INTT performance on the Gem 5 03 processor compared to the Xeon Gold. At the bottom, you have again the peak performance, and at the top you have the speed up for all of the different configurations that we tested. One thing we notice is that despite the fact most of our configurations have lower vector performance, they do outperform it in terms of speedup. So we have less computational power, but greater speedups. We also see that the vector length seems to improve performance. So the first one is one 512-bit unit. Then we test 2 of these units. And you'll notice that, of course, has a peak performance of 32. And we also test one 1 kilobit unit, which has the same exact peak performance, but it does seem to improve the NTT INTT speed up. So it might be more efficient to issue less instructions with a larger vector length, despite the fact we have less units. And we also see some diminishing returns. If we increase the unit size further, we see that the performance does not scale proportionally. So at this point, we're probably hitting a memory bound. We're starting to become memory bound, and so it does not make sense to increase at least the computational performance any further here. Here we have the speedups within OpenFHE. So these are very simple applications in which we just do an encryption, an operation, and a decryption for P equals 16K. And this is running on the VPU. So for the first test, we actually don't perform any operations, just encrypt, decrypt. The others do addition, subtraction, multiplication, and rotation. And we see that we have good speedups across the board in the whole application context for a variety of schemes. Here we test CKKS, BFV, and BGV, and all of them provide good speedups. Still in OpenFHE, here we have a multiplication chain. This is again on the VPU, and we determine the maximum speedup given the fraction of time occupied by the NTT and the INTT. And with Amdahl's law, we determined what the maximum speedup would be. We see it ranges between 2.4, 2.7, and our actual speedup ranges between 1.8, tending towards 2. So as the number of multiplications increases, as the depth increases, we require further and further bootstrapping calls. And as that happens, we also see the performance increasing substantially. So lastly, in the OpenFHE speedups, we have a 3-layer neural network test. So we have a network with 3 layers that are fully connected. The ReLU activation of each neuron is done using a Chebyshev approximation. And here we vary the network layer size in the x-axis in order to test multiple sizes of the network. And here we compare the speedup of our OpenFHE backends running on the VPU with the Intel Hexel backends running on Xeon, all within OpenFHE, of course. We see that it provides significantly better speedups. We see that it seems to tend downwards, but it plateaus. So, and this does make sense as the multiplication depth stays the same, even though the network layer size increases. And so the proportion of time occupied by the NTT and INTT decreases. And so given that we're only accelerating that portion, it makes sense that the speedup would be reduced slightly. Here we have a comparison with other approaches. So these include software, custom RISC-V instructions, application-specific accelerators, and GPU implementations. So here we are comparing with with architectures that that are typically designed for PQC, so there's not much work in terms of FHE acceleration on RISC-V Vector. But most of them are designed as a consequence for lower values of P and Q, and these their respective functional units are designed with those values in mind. And so, if you wanted to increase the P and Q to values that are realistic for FHE, then you would incur an additional resource overhead, which is already quite significant for these architectures. So if you want to use RISC-V architectures with custom instructions, you can get reasonable speedups. However, those architectures will, of course, have limited availability compared to a very general purpose RISC-V vector implementation. If you wish to use application-specific accelerators, of course, these are going to have really exceptional speedups, but they don't have any general-purpose functionality. And so the advantage here is that the VPU can, of course, be reused for any other workloads. And we also see they occupy a very significant area compared to the VPU. The VPU achieves quite significant speedups for a very small area, and, of course, retains general-purpose functionality. GPU implementations are, of course, also great in terms of speedup when you batch a number of NTT and INTTs together, but they do have very high latency compared to our approach, and so it's a trade-off that you would have to consider. We have a number of publications on the subject. So the first one is this work that I'm presenting, which we published at CHES. And we also have NTT architectures for RISC-V processors for fully homomorphic encryption. So those are other works that you might want to take a look at. So to conclude, we presented vectorized implementations for Cooley-Tukey and Gentelman-Sande, which, due to their varying memory accesses, leads to some poor vector utilization in some stages, so the performance is not incredible. However, the Korn-Lambiotte and Pease INTT, which are less commonly seen in state-of-the-art libraries and so on, they do have constant memory accesses, which make them quite efficient and allows us to have full vector utilization in our RISC-V accelerated code. Our speedups surpass Intel Hexel, which is a state-of-the-art x86 library, despite the fact that our architectures that we tested on have significantly lower peak vector performance compared to the Intel processor. In a full FHE context, we also get significant speedups. So in the multiplication chain, we saw almost a 2x speedup, as well as in the neural network test. And in the future, we would like to complete our OpenFHE integration. So currently, it's not a formal backend that you can configure FHE with, but that's something that we are looking into. And we will also like to explore further algorithms, for example, using a higher radix or trying to fuse some of the stages together. So thank you for attending. If you have any questions now, I'll of course be glad to answer them. We also have an artifact available at this QR code here or at this link that you can check the work at.